Hello everyone. Welcome back to another week of Physics 40B. For the past few weeks, we have covered oscillations, traveling waves, and standing waves. In the next few weeks, we will be transitioning into thermodynamics. But before we move forward, we must first cover some basic terminology and definitions from chemistry. If you have already taken a previous chemistry class in high school or college, this video should just be a refresher. The material from this video is adapted from Chapter 18, A Macroscopic Description of Matter, in your physics textbook. With that, let's begin. When it comes to chemistry and thermodynamics, it is important to first understand the microscopic motions of atoms and molecules that affect larger macroscopic properties, which may include pressure and temperature. For instance, if you have a closed container filled with gas molecules, what happens when it is heated on top of a stove? Well, on the microscopic level, the gas molecules vibrate a lot faster and bounce all around inside the container. This is because the thermal energy of the stove becomes kinetic energy of the gas molecules. On the macroscopic level, we know that heating the container simply increases the temperature. In this video, we cover the macroscopic motions of atoms and molecules, as well as begin to dive into the macroscopic property of temperature. Although we will not cover everything from macroscopic properties, we will go over more in detail about pressure and temperature in the next video. Now we will talk about some definitions regarding atoms. In essence, an atom is a particle of matter that defines a chemical element. The structure of an atom consists of protons, neutrons, and electrons as shown in the figure. Typically, an atom is a pure substance that can be found on the periodic table. Next is density. We have covered density when we talked about fluid mechanics. Remember, density is simply the mass per unit volume, which is an intrinsic property of how compact a substance is. There is also another form of density, in which we'll call number density. Number density is basically the number of atoms per unit volume. In the equation, capital N represents the number of atoms. We can also compare the units between number density and density itself, as shown. Avogadro's number is a number that is used to convert between the number of atoms to the number of moles. This constant is given as 6.022 times 10 to the 23rd atoms per mole. If we know the number of atoms, or capital N, we can determine the number of moles in a substance, or lowercase n, which is shown as the equation below. The atomic mass unit, or AMU, is essentially a unit mass of an atom. It is the sum of the number of protons and the number of neutrons. The AMU also only involves protons and neutrons because they are considered to be the heaviest subatomic particles and are concentrated at the center of the nucleus of the atom. The size and mass of electrons are much smaller, so they can be neglected when it comes to considering the atomic mass unit. Moreover, the molar mass is the mass in grams of 1 mole of a substance. For a water molecule, since we know that there are 2 hydrogen atoms and 1 oxygen atom, we can determine its molar mass. Since the molar mass of 1 hydrogen is 1.008 grams per mole, it should be doubled since there are 2 hydrogen atoms in water. Then you can add it to oxygen, which becomes 18.016 grams per mole. Returning to the concept of number density, we can use some equations we have just learned to manipulate it into a new equation. Remember, density rho is equal to mass divided by volume. If we divide mass on both sides, we get 1 over v is equal to rho over m. Therefore, we can substitute 1 over v into the number density equation. We also know that the number of moles of a substance is equal to the number of atoms divided by Avogadro's number. We can rearrange this equation to isolate the number of atoms, or capital N, and substitute it into the number density equation. Since we know that the molar mass is equal to the mass of the substance divided by the number of moles of the substance, the molar mass becomes the denominator of the number density equation. The new equation for number density is the density of the substance times Avogadro's number divided by molar mass, as shown in the bolded equation at the bottom of the slide. When it comes to solving problems, temperature is typically converted into an absolute temperature scale, which is in Kelvin. To convert from degrees Celsius to Kelvin, it is simply the addition of a value of 273. So where does this value come from? This concept stems from the idea of absolute zero, which is considered to be the lowest temperature that is theoretically possible. It is at 0 Kelvin, or negative 373 degrees Celsius. This also means that there is no thermal energy remaining in the substance. When it comes to substances, they can be in the phases of solids, liquids, and gases. From experience, we know water freezes at low temperatures to become ice and heats at high temperatures to become vapor gas. However, pressure on the substance is also influential as well, which is also regarded in the phase diagram. Here is a phase diagram of water. As we can see from the axes, temperature lies along the x-axis, whereas pressure is on the y-axis. Here, we can also see arrows pointing from one phase to another. These arrows are called phase changes. For only 3 states of matter, there are 6 types of phase changes: melting, freezing, vaporization, condensation, sublimation, and deposition. There are also 2 main points that must be considered in a phase diagram: the triple point and critical point. The triple point is a point where the substance embodies all 3 states simultaneously, as a solid, liquid, and gas, as they coexist in some equilibrium. As we can see from the phase diagram on the previous slide, the triple point only occurs at a specific temperature and pressure. On the other hand, the critical point is a point where the substance is indistinguishable in its liquid and vapor forms. In other words, if both the temperature and pressure of a substance becomes too high and surpasses this critical point, then you cannot tell the difference between those 2 phases. That is all for the first part of this chapter. As we have mentioned earlier, we are transitioning into thermodynamics, which requires fundamental knowledge of chemistry. I hope this was helpful to you, and if you have any questions, please feel free to leave a comment down below or stop by our SI office hours. Thank you and take care.